Okay, so we are continuing with experiment 2, where we're exploring how acceleration depends on mass when we hold the net force constant. By this point, you should have at least 6 values in the table at step 21. And so we need to make a graph of this data. Now you can use the graph paper that's provided for you, or I'm going to use Microsoft Excel, and you can follow along with me to do that. So I'm going to work in the same Excel file that I used for experiment 1. In fact, maybe I will come over here to row 1 and do a right mouse click and insert a row so that I can label my first data table as experiment 1. This was acceleration versus net force while mass was held constant, just so I don't forget. And then I'm going to come over here just somewhere to the right, and this is where I'm going to put the data for experiment 2, which is acceleration versus mass while net force was held constant. Okay, so I'm going to start over here. And so I'll just come over here to the right. I'm setting up the data table. My independent variable goes on the left, and that in this case was mass measured in kilograms. My dependent variable is still acceleration measured in meters per second per second. Okay. And so now I'm going to put this data, I thought I had it copied, but I don't. Let me just come over here and grab it. Okay, so type in your data for all of your values of mass, and then we want to get a scatter graph. So I'm going to select my data, and I'm going to go insert a scatter plot just to see the data points. And look at this. It is a nice curve of some sort. And let's go ahead and nicely label this. My independent variable was mass in kilograms. Dependent variable was acceleration. Okay. So goodness, we can tell that this is not a linear graph. And of course we want to be able to fit an equation to this data, but it's going to be difficult to do unless we can linearize it. So the first step that we need to do is to identify the type of relationship. So I'm at step 24, and it says refer back to the reading. This is from Unit 1 on linear models, the reading on linear models. So I'm going to go look at that. This was the reading. This reading is found either in the Resources tab of PowerSchool. It is also found in the Unit 1 chapter under linear models. And so I'm going to go all the way down to section E, the last section of this document, because in section E it talked about how to linearize curved relationships. And in this section there's a table which shows us different shapes of graphs, and we need to find the one that corresponds to the graph that we just made. So I'm going to go back and look at the graph we just made, and I can see that it has this kind of shape. That looks to me to be very similar to this, which says y is inversely proportional to x. And so this table tells us that if we want to linearize this, we need to graph y versus the inverse of x. Okay. So I think we've just found the answers to these first couple of questions. Acceleration that's our y variable, is inversely proportional to mass. That was our x variable. Okay, so it looks like that inversely proportional relationship. And so in order to linearize this data, we need to make a table that has the inverse of mass. If we take the inverse of mass, the units would be 1 divided by kilogram, okay, versus our acceleration. So we will not be changing any of the acceleration data. And for every case, we're going to take the inverse of mass. Okay, I'm going to do this in Microsoft Excel, and I encourage you to do this as well. You could do it by hand, but I'm going to come over here in Excel. I'm going to copy my original data table. I'm just highlighting it and doing a Control-C, and then I'm going to come over here to the right and paste it in here. I'm going to delete the values of mass because I have to change that. I'm going to transform it by taking the inverse of mass. Inverse of mass, and I know the units now will be 1 divided by kilogram. Okay, I'm going to just make my column a little bit wider here so that I can, and in fact I'm going to wrap it so that, okay. So I want to calculate the inverse of mass. I could do this with a calculator. I could take my calculator and say 1 divided by 50, 1 divided by 90, and calculate those values. But I can also tell Excel that I want it to calculate this for me. So to put a formula in Excel, remember we start with an equal sign. See how it's starting to build a formula up here in the formula bar. I want to just take 1 divided by, and then I'm going to bring my cursor and select the first value of mass. So I'm going to click here where I have the 50. When I do that, it puts the cell address, you know, it's column N, row 3. That's where it finds the first value of the mass. And that's all I want it to do is 1 divided by 50. I'm going to hit the Enter key, and it has calculated that for me. Now I need to copy that same formula down this column. And one easy way to copy that, I bring my cursor into the cell that has the formula. I bring it into the lower right-hand corner. See how the cursor changes? Here it's a big white cross, and when I bring it in the corner, it becomes a black plus sign. Okay? Once I have the black plus sign in the corner, I double-click the mouse, and it just copies that inverse formula down. So it knows enough that, you know, for the next column, it says 1 divided by N4, right? At the bottom, it's doing 1 divided by N8. So it is calculating the inverse of all of my masses. Okay, once we have transformed the data this way, we need to get a scatter plot. And so I'm going to go back and highlight those values and insert a scatter plot. Oh, look at this. It's so pretty. Now we have a linear relationship, right? A linear graph. And so we're going to be able to, not sure what's happened to my things here. Let me go back and, well, I'll go to Design and do a quick layout on it. There we go. Okay, so we've got a nice linear relationship here, and I want to label it. So this is acceleration versus the inverse of mass, right? And so now on the x-axis, my independent variable is no longer mass. It is inverse of mass, and the units are 1 over kilogram. But I still have acceleration on the y-axis. Okay, and so now I need to find the slope of this graph. And I can use 2 points from this. I mean, since every single point here it seems to very clearly be on the line, then I think it would be safe to just use any 2 of these points to calculate the slope. And I'll let you do that because I know you know how to calculate the slope. Okay. By the way, if you want, I'm not sure why it's not showing me grids here, but if you click on one of the numbers for this x-axis and do a right mouse click, we can add major grid lines. I just think that makes the graph look a little bit better. Okay, so we've got our graph. You can find the slope. Let's see what the next step is in the lab. We're all the way down here to step 28. It says simplify. Well, you're going to write a physics equation. By the way, in step 27, for this graph, we have acceleration versus the inverse of mass. So your physics equation, acceleration is going to be your dependent variable. You're going to have your slope. We haven't found that. I'll let you do that. But the independent variable is no longer mass. It is 1 over the mass, right? We had to take the inverse of the mass. And so make sure that you use inverse of mass now for the physics equation. And we need to simplify the units of this slope. So let's go look at the graph again and get, it's going to be meters per second squared over 1 over kilograms. Very complicated units, but we're going to just, use our rules of algebra to simplify these. So since I'm dividing by a fraction, I'm going to simplify this by multiplying by the inverse of that denominator. Okay, so I've got meters per second squared times kilogram. Okay, and let's see. Oh, look up here where they're telling me that a Newton has the dimension of kilogram times meters per second squared. Isn't this a kilogram times a meter per second squared? So this is a Newton. The units of this slope of the acceleration versus inverse of mass, it simplifies to newtons. Okay. Then in step 29, they give me some additional data. They've replicated the experiment, okay, or I've replicated it for different values of net force. You just found a slope if you use a net force of 400 newtons. But what if we used 100 or 300 or 500? We get different values. Oh, by the way, this should be 1 over kilogram. See a little mistake here. We get different values of this slope. So let's look at this. I'm going to fill in. So our net force was 400, and I would fill in the slope of that acceleration versus inverse of mass graph. And looks like probably we got 400, I hope, as our slope. And so isn't this cool? In every case, when this experiment was repeated, the slope of the acceleration versus the inverse of mass graph equals the value of net force that was the constant in that experiment. And so we can draw some conclusions about the physical significance of the slope, right? The slope of the graph of acceleration versus the inverse of mass equals the value of the net force, which was held constant in the experiment. And experiment 2 was repeated 4 times, and in every case, the slope of the linearized graph of acceleration versus inverse of mass equaled the value of net force. Also, the units of the slope simplify to be newtons, which is the unit of force. Okay, so we have 2 pieces of evidence here. There's the fact that when the experiment is replicated 4 times, in every situation, the slope of acceleration versus inverse of mass equaled the value of the net force. And then also the evidence that the units of the slope simplify to be the units of force. Okay, so that's 2 pieces of evidence we can cite. And so if we want to restate that physics equation from up above, then that would be acceleration is whatever our slope was times 1 over mass, but we said that our slope equals the net force. So we're going to replace that numerical value with what the slope means, which is net force. So acceleration equals the net force over the mass. And this equation is called Newton's second law of motion. By the way, did you notice that we got the same final equation both in experiment 1 and in experiment 2?